So we're going to continue with stereoisomerism, and we're going to focus mostly on optically active compounds. And so the way that most of these compounds are characterized is by looking at how they rotate the plane of polarization of polarized light. And so you have to first think about what is polarized light and what is the plane of polarization of polarized light. And sometimes this is a little bit difficult to conceive, so I'll give it a shot, and I would urge you also to look at the video that I'm going to make on molecules and the plane of polarization of polarized light, and give you a few demonstrations, and hopefully those demonstrations, combined with what I say here, combined with what's in your book, you'll be able to understand it, at least somewhat. So here is a schematic of just light, not polarized light, and it won't have a plane of polarization of polarized light, therefore. So a light ray, each light ray will have an electric field and a magnetic field. So this is called electromagnetic rays. And so you can see that if the electric field is represented by the red wave here, the magnetic field is perpendicular to it, and it's represented by the blue. And so this is just one ray of light. And so each ray of light will have not only this electric wave, but it will also have the magnetic wave, and it will have an electric wave and a magnetic wave, an infinite number of these. So it will have the electric wave residing in this plane, and then it will have an electric wave residing in another plane that is just slightly rotated out, and then it will have another electric wave residing in a plane that is rotated a little bit more, and then another one residing in a plane that is rotated a bit more. And there's actually an infinite number of planes that pass through, that go from left to right. And so that ray of light, which is not polarized, will have an infinite number of these planar electric waves and planar magnetic waves. And so you can think of it as you know, going toward you, coming in this direction here. And so when you listen, when you see the demonstration that I give you, hopefully you'll understand this a bit more. So you could think of this, when you have this, you could think of this as being just the light that is in one plane. So this would be what it looks like after it's been polarized. And I'll show you what polarized light looks like in a minute. So, you could stop this video and go look at that video before we continue if you wish. So this is the light beam. So here's another drawing that shows you what this shows you better what I'm going to demonstrate for you. If you have polarizing lenses, and this would be a polarizing lens, and this is a polarizing lens. And so this would be your unpolarized light source over here. And see how it shows these in all different planes. And so these would represent the infinite number of planes of the light that come from that light source. And so when it passes through this polarizing lens, you see the little slits here going from top to bottom. That's supposed to represent the fact that this is polarizing, and all of the planes of light that are coming from that light source are going to be screened out except for the light that is just in one plane. And so that's what is represented here. It's just the part of the light beam that is just in one plane, and it will continue on down toward the viewer. And then notice that this polarizing lens has the slits lined up the same as this, so it's exactly parallel. And so the light beam that passed through this polarizing lens will come on down and pass through that polarizing lens, and it will come out the other side, and then the viewer will see that. So the viewer will see the light. In your eyes, you cannot tell that it is polarized light. You cannot distinguish between just this light and the polarized light with your eye. You cannot tell the difference. But there is a way to tell the difference, and I'll demonstrate that for you in the other video. So over here, now let's consider a somewhat different situation. You have the light source with the light in an infinite number of planes here. It passes through the polarizing lens, exactly the same as over there. You get polarized light where the light is just in one plane, just like here. But now, notice the slits. The slits here are no longer going up and down. The slits are going from left to right. So this polarizing lens has been turned by 90 degrees. And so what happens is when this light beam in this polarized light beam, which is lying only in one plane, comes down here and hits this polarizing lens, nothing will come out the other end. So when you're looking at this, all you see is darkness. You see no light, because all of the light except for the light in this one plane was screened out here, and now down here, the light in that one plane is screened out. So you see no light at all. You see nothing. And so this is used in a polarimeter. These two polarizing lenses are used in a polarimeter. And I'll show you how in just a minute. So now here we have the light source, just the same as before. We have the polarizing lens, called a polarizer also. And so now we have a tube. This is typically 10 centimeters long, a decimeter. And now we have another polarizing lens, just like that one, except it has some metrics here. And so what happens is this, let's say that it's filled up with nothing, it's filled with air, then the light that is polarized and is in this one plane will come down here and it will still lie in this same one plane. However, if this polarimeter tube is filled with an optically active compound, that optically active compound will turn the plane of polarization, that's this plane right here, of the polarized light, it will turn it, and when it comes out here, it won't be in the same plane. It will be in a slightly different plane. You can see now it's lying in a different plane. And the amount that this is turned depends on the optical activity of the compound that is in here. If it's not optically active at all, then the light plane that comes in will be exactly in the same position as the light coming out. It will not be turned. The plane of polarization, of polarized light, will not be turned. However, if it is optically active, that plane of polarization of polarized light will be turned. How much? You can turn this dial and see how much. So how much do you turn the dial? You have to turn this dial until you can see light again. And when you can see light again, it means that you have turned this so that these slits exactly match that plane and the light is coming out. And so that's how you measure the amount that your optically active compound turns the light that is coming through the sample. And so you measure it in degrees. Remember, there's 360 degrees in a circle, and so it is typically measured as plus up to 180 or minus to 180. And so there's the 360. Enantiomers rotate the plane of polarization of polarized light to equal degrees, but in opposite directions. So the one that has, say, the R chirality might rotate it in positive or negative, but the other one will rotate it, the S enantiomer will rotate it in the opposite direction. And just because it's R, it doesn't mean that it's always going to rotate the plane of polarization of polarized light so that the degrees are positive or negative. There's no relationship there. You have to measure it every time using the instrument. The amount depends on the sample concentration and the path length of the light, but it also depends on the compound. Some compounds will rotate the plane of polarization of polarized light a lot, and some will rotate it only slightly. And so you have to measure it to know. So the standard measurements are here. The specific rotation is always given in brackets, and it's given in alpha. So alpha, if you see the alpha in brackets, that means specific rotation. And that tells you what's the alpha. This means the rotation of light for that one compound in that one measurement. At a specific concentration, which is 1 gram of compound per ml. That's what this concentration is. And the length is 1 decimeter, so 10 centimeters. So the specific rotation is determined by taking the actual rotation from the polarimeter of the sample that you mixed up, so that the sample has 1 gram per ml and the sample tube is 1 decimeter long. So this is a linear relationship. These are linearly related. Now, the rotation is also dependent on the temperature and the wavelength, but not linearly related. And so you don't see the T or the lambda up here in the equation. And so they're typically given at the end of the specific rotation. So if you look this up in the literature, you'll see a number here for the specific rotation, and it means in those units. But you'll also see the temperature and the lambda, the wavelength, given here outside the bracket. So these are not linearly related, so they're just given so that you know that if you go in and you're going to measure the optical activity of a compound, you need to do it at that temperature and using that wavelength of light if you want to reproduce what's in the literature, which is always a good thing to do first before you start. So let's look now at 2-bromobutane. Let's just go back and check. So this is this R, 2-bromobutane. Yes, 1, 2, 3, 4. That's 2-bromobutane. And so here we have hydrogen going back. And so the prioritization is bromo over ethyl over methyl. Okay, so we're going clockwise. Yes, that is indeed the R isomer. And so this is going to be the S isomer. When this was measured in the polarimeter at 20 degrees and using the sodium D line as the wavelength, the rotation was found to be minus 23.1, and that would be 1 gram per ml in 1 decimeter solvent sample tube. And so this corresponds to that compound, and notice this one, since this one is negative, that one has to be positive. This one corresponds to that, okay? So they're going to be in equal but opposite directions for rotation. Now, the minus means that the light coming out of the tube was rotated in the negative direction, counterclockwise. This means that the light was rotated in the clockwise direction. That's what this means. And this negative and the positive, have no correlation whatsoever with R and S. It will always be negative for this particular compound, but just because, I mean, if you put chloro up here, it doesn't mean that it will also be negative. Okay? You can't say that R isomers will always give a negative value in the optical activity. That is not true. You don't know until it's measured. Now, there is one other thing. Sometimes abbreviations of dextrorotatory and levorotatory will be applied to the optical activity. So a lowercase italicized D, will correspond to the positive rotation, and a lowercase italicized L will correspond to the negative rotation. So, yes, the D and L do correspond to positive and negative respectively, but they have no correlation whatsoever to S and R, just like these have no correspondence to S and R until they are measured for that particular compound. Once you know that this was measured, and here the plus corresponds to S, it will always, this compound will always be positive. But other compounds that happen to have the S configuration will not be positive. I hope that's clear. Okay. Rotation is called dextrorotatory, positive is called dextrorotatory, and negative is called levorotatory. And sometimes these are abbreviated with D and L, lowercase italicized, D and L. The compound below has the S configuration. So let's look at this. Hydrogen is going back. So let's characterize this. So the highest priority is going to be nitrogen. What's next in prioritization? Carbon-bearing oxygen will come before carbon-bearing hydrogen. So this is 1, 2, 3. So yes, it is counterclockwise. It is indeed S. Now, this optical activity, the rotation, is L at 20 degrees centigrade, but it's D at 100 degrees centigrade. So there's, like I was saying, there is no correspondence between temperature and wavelength. So there's no linear correspondence. And so those are not included in the equation. They have to be given, but not included in the equation. And that information, you have to either get it from the polarimeter by measuring your sample, or you have to go look it up in the literature. A lot of those are reported in the literature. The magnitude and direction of optical rotation can't be predicted. You have to measure it experimentally using the polarimeter. But you can predict the rotation of a racemic mixture to be 0 because the R and S isomers rotate the plane of polarization of polarized light equally in opposite direction. And so if it's 50-50, they're going to cancel each other out exactly. And a 50-50 mixture is a racemic mixture. So there you have it, a 50-50 mixture of the two enantiomers. Half and half will be racemic, and it will not rotate the plane of polarization of polarized light. However, if it's not 50-50, let's say it's 55-45, it will rotate the plane of polarization of polarized light if they are optically active. You know, it's not necessary that a chiral compound will always be optically active. But if it is, it will, if it's not 50-50, it will rotate the plane of polarization of polarized light. Okay, and so if one enantiomer is excess, then is present in excess, then you can actually calculate how much of it is in excess. So here's an example of that calculation. So once again, here's the specific rotation that is given. The alpha is the specific rotation because it's in brackets, 20 degrees centigrade, and using the sodium D line, which is a very specific line, wavelength of light. And so this gave a specific rotation. That means 1 gram per ml, and 1 decimeter sample tube. And so that's not even given here. You're supposed to understand that by the brackets around that alpha. And over here, the other enantiomer is the same number except different directions. And so a 50-50 mix will give you 0 rotation. Now, what if one of these is present to a greater extent than the other? So here, we say that there's a mixture of R and S. It has a specific rotation of 4.6 degrees, but they're not telling you which one is present in excess. Can you tell which one is present in excess? Absolutely, you can tell that immediately by that negative sign. The fact that that is a negative sign means that that mixture has more of this than that, because this is the one that has the negative sign, and you don't have enough of this to cancel that out. So you've got more of this R isomer than the S isomer, okay? This is the R, that's the S. You have more of this. You can tell it because that is negative and that's negative. So how much more? You look at what's observed, that's this, 4.6, right here, this is what's observed, and you look at the alpha of the pure enantiomer, that's this, the minus 23.1, okay? This is what you would have if you had pure. So you have 4.6 divided by 23.1, and you convert it to percent, and when you do that, you say, you know that you have 20% EE of that. So that tells you that you've got a 20% excess of that. That means that the other 80% is a mixture. So you've got 80% that's a mixture and 20% of that in excess. So that tells you that you've got 20% of that plus 80% divided. That means 40% of this and 40% of that. So you've got a total of 60% of that and 40% of that in your solution. And so you'll be working some problems like that in your homework problems. And this is the best explanation that I can give. So enantiomers and diastereomers, remember you've got constitutional isomers, they have a different connectivity. Stereoisomers, which have the same connectivity, but the groups point in different directions. They have a different spatial relationship. You have enantiomers, which are mirror images, non-superimposable mirror images, and then everything else, all other stereoisomers, which are not mirror images, are diastereomers. They are non-superimposable and not mirror images. And so we're going to see some examples of these also. So look at these. These are not superimposable. They are not mirror images. They are diastereomers. Okay, and this is cis-2-butene and trans-2-butene. We've gone over these. These do not have identical physical properties. They have different physical properties. Enantiomers will have the same physical properties except for their optical activity, and a few reactions in special cases, which we will consider at the end of this chapter. Now, stereoisomeric relationships. Notice that this is a mirror image, this is a mirror image, this is a mirror image, This is a mirror image. So this is an enantiomeric pair, another enantiomeric pair, another enantiomeric pair, another enantiomeric pair. This is in your textbook. I urge you to look through these. Look at the designation of the chiral centers here. Look at them here. Look here, here. Look at all 8 of these. There are a lot of things that need to be said about this. First, you'll need to do the numbering correctly. You have to look at this and see which is the highest priority group. The highest priority group here is the alcohol functionality. And so carbon 1 will be the carbon that bears the alcohol functionality. So you number around the ring in a manner to give the substituents the lowest possible numbers. So this is going to be 1, 2, 3, 4, 5, 6, but you don't care about that. Here you care about 1, 2, 3. And the chiral center here is going to be R, the chiral center there. It's going to be R, the chiral center here. It's going to be S, so it is 1R, 2R, 3S. And if you were naming this, you would have parentheses around these, followed by a hyphen and followed by the name of the compound. Okay, and the name of this compound would be 3-chloro-2-methyl-cyclohexanol. And it would be preceded by these, because these tell you that whatever's at the 1 position, this carbon has that R configuration. The carbon at the 2 position has the R configuration. The carbon at the 3 position has the S configuration. I urge you to go through and work through all 8 of these. So now, what you have, this is an interesting thing that the author uses. He said, think of this as twins, 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 and twins. The relationship of this compound to the other compound is like a twin. And the relationship of this compound to all these other 6 is like siblings, but not a twin. So this compound would have a total of 7 siblings, but 1 twin. One of those 7 would be a twin. There's another interesting thing that is demonstrated by these 4 pairs of twins and these 8 stereoisomers. So, and that is, look at the number of chiral centers. 1, 2, 3. So the number of chiral centers, let me put it like, can be used to calculate for you the maximum number of possible stereoisomers. And the way that that is calculated is it is 2 taken to the nth value. Okay, so here this is 1, 2, 3. So that would be 2 cubed. 2 times 2 times 2. And so 2 taken to the 3rd power. So 2 times 2 times 2 is 8. And indeed you see the 8 here. And 8 is the maximum number of stereoisomers. You're not always guaranteed that you will have all 8. There may be a situation in which one of the pairs has a mirror image in there. It actually has, is the same compound. And so that will cut down your number of stereoisomers. So that equation, 2 to the nth power, gives you the maximum number of stereoisomers. It doesn't guarantee you're going to have all of those. It just predicts the maximum number possible. So here is that equation. The maximum number, maximum is a key, of stereoisomers is given by the equation 2 to the nth power, where n is the number of chiral centers in the compound. So what about this compound? Let's look at this. Where are your chiral centers? 1, 2, 3, 4, 5, 6, 7, 8. This is not 1 because the 2 methyls are the same. So this is 2 to the 8th power. In cholesterol, what's 2 to the 8th power? So you ought to calculate this. I can tell you it's 256, but go through this, do this yourself so that you can feel confident of it. Symmetry and chirality. So any compound with one chirality center will be a chiral compound. Doesn't necessarily mean it's optically active. With more than one chirality center, a compound may not be chiral. It could have a plane of symmetry, just like this one does not have a plane of symmetry. This one has two chiral centers, and it will have an enantiomer. This one has two chiral centers, and it has a plane of symmetry. This one will not have an enantiomer. Okay, so this is a case where you're going to have two chiral centers. 2 to the second power is 4. 4 is the maximum number of stereoisomers you could have in this compound, and you will have 1, 2, 3. You will have only 3. You don't have the total number of possible stereoisomers predicted from that equation. Okay, so here the plane of symmetry is demonstrated. Okay, this one is chiral, that one is not. This is called a mesocompound. Mesocompound. Okay, if it has a plane of symmetry and it is its own mirror image, it has a mesocompound. If there is a mesocompound present, then you're not going to have the maximum number of stereoisomers, because one of those pairs will be represented by one mesocompound. This is achiral because it has a plane of symmetry. It is not a chiral compound. Achiral means not chiral. If a compound has a plane of symmetry, it's achiral, which I just finished saying. But it could also be achiral because it has a point of inversion. Okay, so here the point of inversion is right in the middle of this molecule. Okay, so, and this is fairly uncommon. Okay, you don't see these very often. So here, if you consider this plane of the point of inversion, as your point of symmetry is right here in the middle, and you think about taking this methyl group through that point of inversion, and it comes out down here. Okay, this through the point of inversion, and it comes out over here. This through the point of inversion, and it comes out over here. So it has a symmetry of inversion. So this will not be a chiral compound. Symmetry and chirality. Overall, the things that you need to remember are the presence or absence of rotational symmetry is irrelevant to chirality. A compound that has a plane of symmetry is achiral. A compound without a plane of symmetry will usually be chiral, but there are exceptions, like you just saw. So up here, what we're talking about right here will be conformers. That's back on the conformers. They're not even isomers. Conformers are not isomers. They are just compounds, rotating about carbon-carbon single bonds. So mesocompounds. So a compound with chiral centers, but it's achiral because of symmetry. Here you have a plane of symmetry, a plane of symmetry, a plane of symmetry. And so these are mesocompounds, and they will have less than the predicted number of stereoisomers based on that 2 to the nth power. So here, 2 chiral centers, 2 to the second power is 4, but you'll only observe 3. Here, 2 chiral centers. Since you have a mesocompound, you'll only observe 3 actual stereoisomers. And the same thing here. 2 chiral centers, you will only observe 3 different stereoisomers because one of those stereoisomers is a mesocompound. So that, in conjunction with the demonstration of the molecular models, which I will make for you, it'll be a separate film, which will go along with this and should help you understand this. And then after this, we're going to have one more video, which will talk about some other specific points of stereoisomers and ways to draw them, and just a few smaller topics, but still important. And I'll create that for you shortly.